What are some of the things that are important to do when you're working with sensor data? And then thinking about other people as well. Like we have a big section in the book about like what does a team look like that's working on an embedded machine learning product, and it includes all sorts of people beyond like the engineers who are hacking away on low level like C implementations of mathematical concepts. So we've got people like product managers, project managers who are working to figure out what to build and organizing how it gets built. Domain experts who understand particular fields and know how we should be applying this type of technology in, or what are the opportunities for applying these types of technology in specific fields like healthcare or industrial automation or you know, anything and everything. And then there's a huge amount of focus on the book around like how do you build effective applications. And this is sort of going beyond like, okay, what is it possible to build technically, and goes into like, what is it possible to build that actually works well in the real world, and what kind of processes do you need to make sure that what you're building does work well in the real world. You can't just kind of grab a model off the internet, squeeze it down onto a device, throw it out there, and you know, you've got a product. You've got to really think about from the very beginning, like how does the thing I'm building interact with people in the real world? Does my data set reflect the types of people and the types of situation that this real world application is going to see? What are my evaluation procedures? How do I understand when my product is working well and is ready to ship? And how can I understand if my product is not working well once it's in the field? And one of the things that, you know, you should be really strict on is like, is this actually good enough to ship? Is this good enough to be a product, or is it going to cause problems because it doesn't work effectively across all of the different situations that it's supposed to work in? So all of this stuff is very far from the initial beginnings of just like, how do we take this pre-trained model and squeeze it down to fit on a microcontroller? But I think this is particularly exciting because even though I do love the low-level stuff and the kind of hardcore ML stuff, what I'd love even more is that we have a world filled with products that are using machine learning on embedded devices. And for that to happen, we need to have participation by a very broad swathe of people who work on building things and researching. And that's something that, you know, we're ready for now, I think, as a sort of little industry. We're ready to kind of blossom into this big thing. So it's really exciting to have all of you here learning about this field. So the next thing we wanted to dig into a little bit is like, what does the future of edge AI look like, right? And, you know, to give the kind of overview of what it looks like today, I think today, this isn't really an emergent technology anymore. It's a fairly established technology, but it's one that has unequal distribution. And the way that looks is that if you have a cell phone, your cell phone has embedded machine learning models running on it right now. Like you know, pretty much all mobile phones right now have models that are constantly running, looking for keywords to activate voice assistants, or looking for accelerometer or IMU data that indicates a car crash happening, or, you know, various other use cases. And we're carrying around these little computers in our pockets that are running edge AI and like what we call tiny ML models, and have been for a few years. So in terms of distribution to a world population, we're almost at like 100%. I don't know what the rate of cell phone ownership is, but it's, you know, it's very, very high. So this isn't a technology that's still, you know, being talked about, but hasn't left the lab yet. It's something that's very widespread, but it's something that's not necessarily reached out into every industry and every vertical and every place where it has the opportunity to make an impact. So What I'm excited about in the near term is we're starting to see that um, impact spread beyond the initial kind of foothold in cell phones and digital assistants. And the two places that we are seeing that most promising at Edge Impulse are in industry, and I'll kind of dig into that, what that means a little bit, and in health and wellness. So those are the two areas that we see most promising in the near term. And I'll add a third there, which is very exciting to me personally, which is in conservation. So conservation was kind of exciting because it was the first place where embedded machine learning was just like a clear brain dead natural fit. You have researchers who are trying to monitor conditions and maybe monitor animal populations or understand what's going on in ecosystems that are far out in the field. So in the middle of the forest somewhere where there's very little connectivity, or somewhere where there's sort of extreme weather conditions, or in places where you need a really lightweight device that will fit around on a collar that goes around the neck of an animal that's being monitored. And so conservation researchers were really early in seeing the potential of embedded machine learning. And there's a whole bunch of really amazing applications and use cases that have been built around things like tracking animal populations and monitoring individuals, like I mentioned. But I think that sort of is a good microcosm to look at, like what are some of the other broader and more commercial things that this technology will impact soon. Because anything that has those same kind of constraints, where you've maybe got connectivity issues, or you have poor access to energy, or you're trying to monitor the complex individual behavior of individuals or the functioning of biological systems. So in industry, there's so many potential applications around things like predictive maintenance. So this is if you're trying to understand if like a machine or a system is operating effectively, and are you able to understand if like a machine looks like it's going to break down soon, so you can do some maintenance before it breaks down and avoid costly stoppage. We've got things like quality assurance. So what if you can use computer vision to inspect things that are coming out on a production line and make sure that they are like not that they're intact and have been manufactured correctly. And automation generally. So like, how can we hook up these feedback loops where we're using embedded machine learning to process sensor data and understand what's going on with the situation, and then use that to control and drive automation of those situations, so that we can basically do stuff that wouldn't be scalable if we were dependent on labor cost. I think that if you think about industrial stuff, that's really what this technology is exciting for, is making things possible that would otherwise be prohibited by labor cost. And so anything which, you could put a person there watching a production line to inspect every item that comes off and make sure you're not shipping anything that isn't perfect. Like that isn't necessarily going to be cost effective if you're trying to manufacture things cheaply. But if you can do that using a computer vision system, then potentially it's within reach now, where it wasn't before. Same with predictive maintenance. Like in a lot of cases, you will have professionals who are walking around a factory floor, for example, and they have really deep experience and understanding of how to interpret what these machines are doing. So you're basically like, if this highly trained and experienced person is present and available, you can understand if there's a problem. But if they're not present and available, you don't necessarily have any insight. So being able to automate some of that insight, work with those experts to capture some of that insight and knowledge that they have, and then distribute it through smart sensors throughout an environment, that gives you the ability to suddenly have insight everywhere where you just couldn't before. So that kind of thing is really, really exciting, and generally gives us all these opportunities to improve safety and productivity in industrial sites, and to reduce costs. And these are the kinds of things that, they may be a bit like unsexy. It's not as cool as like a, fancy new wearable or a consumer gadget. But to me, these are like by far the coolest things, because we're just incrementally making our entire industrial system more efficient, safer, more effective, potentially more sustainable. And just making these little improvements across the whole world leads to massive improvements as a system. So the other topic that's really exciting is health and wellness. So we are these complex systems ourselves. Like a human body is, the most sophisticated machine that we know about, aside from the ecosystem that we live in, I guess. And understanding our health and what our bodies are telling us can massively improve people's lives. So at the one end, you've got things like fitness and health trackers that people use on a kind of consumer basis to understand, like, is their workout plan having an impact? How can they train better and avoid things like injury? And then at the other end, we've got medical applications where we can actually help people understand, or help their physicians understand what's going on in their bodies, how are therapies being effective, and potentially even building devices that can assist with therapies. So the real thing there is, how do we help people feel healthy in the least intrusive way? So there are lots of ways that, you can monitor your body and give insight to your doctor or to your personal trainer that maybe aren't practical because they're so intrusive. So for example, if I was going to do some kind of like bank of tests every hour of the day, and then give that data to my doctor, maybe my doctor could have some useful insight into my health and how it's changing over time. But obviously that might get in the way of my work a little bit and other stuff I'm trying to do. So what would be really cool is if you can use the ability to interpret sensor data on device to put some of that capability into a wearable, and allow people to get this type of insight into how their body is working, and share that with their physician or use it for their fitness goals without having this incredibly intrusive process involved. So that's what's very exciting. It's sort of technology allowing us to be more humane and fit better into people's lives, which I think a lot of this is really valuable for. It's not about creating these new weird technology systems that then we adapt our lives around. It's about building things that fit better into the lives we want to live. And I think that's why the embedded machine learning has such promise, because it makes us better able to do that. So Jenny, I don't know if you wanted to jump in there with any thoughts. Otherwise, I'll jump onto my next bullet.
Well, we did have a question from the chat. If you had any thoughts specifically about automotive applications, and specifically they had a question about driving monitoring systems. I do know there is edge machine learning in a lot of these applications, like with Tesla, but I'm not sure if you have anything on the top of your head that you can comment on there, Dan.
Yeah, absolutely. So I think the self-driving cars are like a classic example of edge machine learning or edge AI. We've got these big systems that have been built that are essentially completely dependent on the fact that they're doing edge processing. There's no way that you can have a self-driving car that is doing its computation in the cloud when it's deciding whether to put on the brakes or not. It's just not safe. So it's a really good example of why this kind of technology is really important. But beyond the sort of the big kind of elephant in the room of self-driving cars, we also have things like ADAS, like automated driver assist systems, which essentially help you out in smaller ways. So for example, making sure that your eyes are on the road and you haven't fallen asleep and trying to wake you up if you have, or allowing you to stay within a certain distance of the car in front and brake in order to keep away. So some of these things, I think, I mean, obviously the automotive companies are doing a lot of amazing work here and have been for a while, and with classical methods for computer vision before we even got to the embedded ML stuff. But one of the things that's really interesting here is it's quite sort of challenging from a regulatory perspective and a safety perspective. There are very high bars for like the quality of the code that you deploy, and being able to do things like static analysis of algorithms is really important, so you can prove that the system's going to behave in a certain way. So while it is possible to use machine learning in these areas, there's definitely some challenge compared to some other usage areas. So I think this is going to be a really important space, but it's not necessarily one of the kind of low-hanging fruit, because there's this hugely important safety aspect that's kind of there from the beginning. So it looks like we had some other questions.
Yeah, I just noticed that we did get the ChatGPT question. So if you want to comment on that, Dan, but
Yeah,
they said that current hype, can you share some accessible ideas on how to incorporate large language models into TinyML?
Yeah, absolutely. So I'll chat about that in a moment. It's sort of already on the list for this slide. But any other stuff that we should go? I think I can just jump into the next thing. The one question, there's a really good question. Oh, sorry, not the next slide, but the next section of this one. But there was one good question I just noticed. How is machine learning related to AI, or what is the difference between them? That's a really good question. So what I would say is this is something that people debate about, and for a long time it was very unfashionable to talk about AI. And recently it's become fashionable to talk about AI again, because of the sort of leaps and bounds that have been made in things like natural language processing. But the difference is AI is sort of this large topic and a very kind of ill-defined topic that is basically about how do we create intelligence artificially. It's like that you then have the problem of like, how do we define intelligence, which is, you know, a topic for philosophers, but a lot of people have spent a lot of time arguing about that. But if you think of this as a kind of broad category of like technologies and approaches that we use to try to create systems that have some intelligence, and to me, intelligence means, this is a definition that I came up with for the book, it means knowing the right thing to do at the right time. I don't think that would stand up in any kind of philosophy debate, but to me, that's what intelligent means. And it means you can look at some inputs and understand what the right output should be. And the difference between that and machine learning is one of many techniques that we can use to try to capture some intelligence. And with machine learning, we capture that intelligence by training a model. So we build a data set that represents our understanding of the world, and then we train a model to give us an output that is based on that understanding of the world. So it's one mechanism for implementing AI, but there are other ways to, you know, create things that we describe as artificial intelligence too. So that's an interesting sort of philosophical thing, but jumping back into like, what is exciting in the future that's coming up soon. So I'd say that like, we're going to see a lot of evolution of hardware and algorithms, and also the tooling that we use those with. So we've already seen like from the beginning of my embedded machine learning journey, we were talking about how do we fit machine learning models onto devices that were definitely not designed to be running machine learning models. Like when this silicon had been developed, it was not because we were going to be running neural networks on it. It was because it's useful to have these capable general purpose processors that can run all sorts of different programs, from the user interface for a consumer application through to signal processing of complex and high frequency signals. We ended up with these general purpose little processors, and then people like Pete Warden had this spark of an idea of like, hey, what if we use these to run deep learning models? But now, a few years later, we are seeing like this kind of Cambrian explosion of different types of hardware that are specifically designed around these kinds of workloads. It's really exciting. We've got like accelerators that are designed to specifically accelerate the type of deep convolutional models that are used in computer vision. We've got devices that are used that are implementing completely new, novel and exciting ways of running deep learning models, for example, using neuromorphic compute. So things like spiking neural networks, which are designed to be sort of a slightly closer approximation of how a biological system of neurons works. And they're really good at doing things like processing high frequency time series. So we're starting to see this hardware that's designed for these tasks. And it's really just the beginning of this insane explosion we're going to see, where now that people know there's a benefit to running these algorithms on highly efficient embedded devices, we're going to see more and more emphasis on producing those highly efficient embedded devices that can run these workloads. And the sky's the limit, right? It blew my mind when we first got object detection working on a microcontroller like a year or two ago. And just to see this thing running at like a reasonable frame rate, it's like, wow, that's crazy. And we're going to see so many of those wow, that's crazy moments over the next few years, where it's like, I can't believe you can have a conversation with a generative text model that's running on an extremely low power chip. I think that moment's coming, relatively soon. So that's super exciting. And going along with that is algorithm development. We previously were doing the same thing. We were taking these off-the-shelf algorithms and applying them to problems on the edge. But an off-the-shelf, optimized for GPU training deep learning model is not the most efficient thing necessarily to run on an embedded device. You might end up being way on the wrong side of like prioritizing memory use over compute, or all the trade-offs that you make might be slightly wrong. So we're starting to see people creating algorithms that are specifically designed to run efficiently on embedded devices. So at Edge Impulse, we came up with this architecture called FOMO, which basically allows you to do a sort of simplified object detection on very constrained devices very fast. So we're going to see more and more of that. And then all of this sort of stuff exists in a world where we need to interpret it in some way to fit the algorithms onto the devices. And so we're going to see a lot of evolution in compilers and deployment tools. Like, how do you take this model, which is basically a bunch of weights and numbers, and make it run efficiently on a device? There's so much work that can be done on the tool chains that make that possible for different devices, so that whatever device you're running on, we're going to be running in the most efficient way possible for that silicon. And then the fourth thing is developer tools. We have really a situation right now where the embedded engineering side is not very accessible for machine learning engineers, and the machine learning side is not very accessible for embedded engineers, and neither of those things are accessible for domain experts who know a lot about a particular application area but don't necessarily know those technologies. So what we're trying to do really hard at Edge Impulse is improve that situation so we can help embedded engineers be productive with ML and vice versa. But there's still, it's a never-ending job of like improving and improving tools. So I think that we're going to see a lot of rapid improvement and rapid change over the next few years on that front. The next thing I talked to there is these large generative models. So we've obviously seen this explosion over the last 6 months of interest and excitement in using models to generate stuff and to understand complex human communication, whether that's speech or text and conversation, or whether it's images and even art and music. So I think this stuff is destined to be at the edge. I think everything is destined to run at the edge because there's such huge benefit to having individual, private, secure, atomic deployments of sophisticated AI and machine learning. So while we've got this situation right now in the cloud, we have these APIs that you can access where you can maybe send some text to ChatGPT and get an answer back. That, to me, that's very much an artifact of this sort of awkward moment in time where the models haven't been optimized for size at all. The data that they use is fully just sort of web data. So it's like text and some still images. But when we start thinking about building systems that can interact with the physical world and actually really do useful, meaningful things in the physical world, we have to start talking about the edge, because sensor data is not really compatible with APIs. We've learned this from the IoT world, that you can't just capture all your data and send it to an API. There just isn't bandwidth. There isn't enough power available at the edge to, drain your battery and send all this data. So if we're not able to run these big models at the edge, they're going to be missing out on all of the things you need in order to function in a three-dimensional world that involves motion and physics and, gravity. And if you're trying to build an intelligent agent that can move around the home and help you out with things, that isn't going to happen if you're depending on APIs. So it's really an inevitability that we push this stuff to the edge. And people are already starting, right? The open source community has taken the Llama model that Meta trained, which is like there's a 7 billion parameter version of this language model. It's not quite as good as ChatGPT or whatever, but it works. And people have been running this thing on their laptops or on Raspberry Pis or other SoCs. And so you can see how much interest there is in doing this. And it's just a matter of time before the hardware and the algorithms adapts and evolve to support these use cases that people want to do. And once we start adding multimodal data, then the sky's the limit. So it's a good question. When you say edge, what do you mean? So that's such like a deeply kind of a term that I'm so deeply familiar with, I forget that it's even a technical term. But what it means is it comes from old network diagrams, basically. So if you draw a diagram of a computer network, you have like the middle parts where all the computers are and the network infrastructure and like the internet and so on. And then at the edge of the network is where all the devices are. So if you're on your laptop, like your laptop is an edge device. It's like connecting to the edge of the network. If you have an IoT device, that's an edge device. So any device that's sort of living connected into the network, and it's not like a server, and it's basically doing something interacting with the real world. And the edge is where all the data lives. So that's why it's so interesting for us. So before we go on to the next chunk, I want to just talk about like how I think this stuff is going to change the world long term, because that's what's really exciting to me. Near term, we're going to see lots of really cool applications in industry and in across commercial applications, and also in science and research. We're going to see all these improvements in hardware and algorithms that are over time enabling us to do more and more exciting and ambitious stuff. And we're going to see these big models come down to the edge. So there's really like not a difference between what you can run on the edge and what you can run in the cloud in the long term. And what I see that doing to our world long term is that we're going to make everything intelligent. I think that we're going to end up, maybe this is not in 10 years, maybe this is more like 100 years or 500 years, but we're going to end up with a world where every single thing that we build understands a little bit about what is its purpose, how can it better help the people and other entities that are trying to use it. If we build a tool, that tool should understand, like, what situations does it work well in, what situations does it not work well in, and how can it adapt to help us and help us have more enjoyable and easier lives, and get the things done that we want to do. So that idea of sort of ambient computing and distributed intelligence, and building homes that respond to us in ways that we would take for granted, that are impossible now. But like, what if I wake up in the morning and my house is at the right temperature and all the correct lights turn on and off as I walk into the rooms, and I've got breakfast waiting when I wake up. Like, that's the most sort of basic, easy to imagine version of this kind of thing. And along with that comes like energy savings, because my heating's not running when it shouldn't be. There's time savings for me because I can, save on walking around the house, turning off all the lights before I go to bed. But very long term, it's like, how do we build a world that is dynamic and is more reflective of the natural organic environments that we've evolved to live in? Like, nature is amazing, it supports us and nurtures us, and then we've built all these artificial environments that we live within. But I think adding more intelligence back to those environments is a way to get back to living in a responsive and beautiful world that we spend more time in love with than being frustrated by. So that's my hope for the future of embedded machine learning and the tools that we build. So for the next section, we wanted to talk about some of the practical challenges and opportunities that exist in this space, and how you can engage with those as you start your journey. And it's the people here in these kind of workshops that are going to be the people who build this amazing future that I'm so excited about. So Jenny, did you want to take the lead on this one, or should I do it?
Yeah, let me just
Everyone's probably sick of hearing me rambling.
Yeah, I'll just start a little bit, I guess, with the business side of our three different subsets that we saw for challenges and opportunities. By the way, everybody, thank you for your great questions in the chat. Happy to discuss more of those at the end as well. But this has been really interactive, and I really appreciate it. But so the first area that we see challenges and opportunities in is the business side of things. So as we discussed earlier, one of the main things is we see a bunch of businesses where they have either they have large amounts of sensor data or image data sets, but they don't know how to apply edge machine learning, or they want to apply edge machine learning, but they don't know how to collect these data sets. So a lot of this on the business side of things is really just identifying these use cases. Once you get into a field like TinyML, what's the phrase, Dan? Once you have a hammer, everything looks like a nail. So it's really determining, what are the most viable nails, and what can be solved by just digital signal processing, for example, rather than needing edge machine learning, or what needs both, and how can we optimize both those areas at the same time. We also see that, there's a lot of data sets that are out there. Like we'll see with competitions on Kaggle, a lot of these IoT data sets are created, which are great for starting off the process of creating an edge machine learning product. But these are not necessarily really high quality data sets. So something that we want to see in the future is like the people at Harvard, they've created MLPerf. So they've created these like master data sets of benchmarking machine learning models on various edge devices, which has been great. But I think there's just a very large open hole there of creating more of these golden standard data sets. And of course, the great thing about Edge Impulse and these tools that are being created in order to train edge machine learning models is that you don't necessarily you won't necessarily need a golden standard data set in order to get started. You only need a small amount of data, and then you can go from there. But it's just a matter of just further increasing the amount of data sets available, and increasing our opening our minds to all the opportunities that are available for applying edge machine learning, because it's almost limitless. There's a lot of things that we've talked about today, especially in terms of wildlife conservation, industrial factory line machine learning applications. But as I mentioned in my webinars and my other talks that I do, if you can think it, if you can dream it, you can likely apply tiny machine learning to it, even if it's not the most efficient way to do it. The opportunities are endless. So I think it's just a matter of increasing the education out there, and just getting started, and just experimenting. Yeah.
Yeah, I think the thing that I feel most sort of pain around in this area with thinking about like building actual products with machine learning broadly, not just embedded machine learning, but broadly, is the more specific your application is, the harder it is to collect data. So if you're thinking about like an industrial application, where maybe trying to train a predictive maintenance algorithm that can tell us when a machine is likely to break down. So we have this horrible problem of like, unlike things like vision, where we've got like this huge open vision data sets available online, there are not lots of huge open data sets with accelerometer data or audio data from machines running in factories, let alone the specific machine that you have installed in your specific location. And so this challenge is really hard for the people who are trying to deploy the technology, given that there's not much data, and that often commercial operators are very hesitant to share data with each other, because you don't want to be sharing your sort of private kind of data about how your operations work with your competitors. How can we enable people to build successful applications when data is the most important thing? And this is very much an unsolved problem. So there are a few different angles. One of them is like, how do we make it easier to collect data? And so that's something that's, you know, definitely a valuable thing to pursue. Like, how do you make it easier to get the data that is there? But you're often going to find that there just isn't enough data by itself. So then we need to think about like, how can we allow you to collect different types of data and make use of that? So for example, collecting unlabeled data and still making use of that through some kind of active learning loop, so that you can, if you're going to spend time labeling data, you'll spend time labeling the minimum amount possible to get good results. And so that's just a huge topic. So if there's one area where you think like, where could I apply myself to like this problem and solve something really valuable, it would be, how could I solve data problems for a particular set of users? And if you can crack that, then you're going to be successful and beloved by millions. So beyond the sort of business side, which is obviously the, you know, important part of, you know, how do we make money and impact the world with this technology? Research is what backs all of this up. And I think the three key areas for research that are exciting, and there are opportunities for all of you, are in algorithms that are specifically designed to work well on edge devices. So that's both the machine learning, like deep learning model architectures, and ways that you process the outputs of models to interpret what they're telling you when they're running on a device, and also signal processing. So digital signal processing is a vital part of embedded machine learning. How do you design these algorithms so that they're giving inputs that are kind of optimal for what these deep learning models are trying to learn? And the next thing is hardware acceleration. So like, how can we improve the hardware that we have so that it's better able to run these types of algorithms that we care about. There's this idea called the hardware lottery that was kind of coined by Sarah Hooker, who's an amazing researcher in machine learning, sort of a focus that overlaps with embedded quite a lot. And she posited this idea that we have a lot of basically reliance on hardware when we come up with ideas. So if you look at what are the big architectures that are popular right now, they're architectures that are easy to train on GPUs. And GPUs are graphical processing units. They're components for computers that were designed specifically to accelerate the computation of things to do with rendering 3D graphics for playing video games. So if you think it just is completely crazy that like cutting edge machine learning is dependent on the hardware and the limitations of hardware that was designed so that like people can play video games on their PC back in the 90s. So what we need to do is kind of unpick those things and start saying, what does an algorithm look like that's designed for running on a microcontroller, not for running on a graphics card? And once we do that, we're going to start having much better results and much more efficient sort of applications. And so the third thing around research I already kind of emphasized is how do we make the most of limited data? So I think that's really by far the most important thing. So the third thing I want to touch on, which kind of brings all this together, is career. So how does this impact on your career? Like if you're early in your journey of thinking about embedded machine learning, how can you end up working in this field? What are the kinds of jobs that are available? What's this going to look like over time? And what are the most important skills? So I'd say there's a huge amount of opportunity here. We are early still in this growth curve of the field. To begin with, you know, there's a lot of people working on this type of stuff, but compared to the number of people who will be working on it 5 years from now or 10 years from now, as all of these industries start adopting machine learning on embedded devices, it's still very small. So I think there's like a lot of depth here, but it's like not something that imminently there's massive numbers of open roles, for example. But I'm very confident in the depth there. And the thing that's really good is that over time, I think it's going to become more accessible for people who have domain expertise in certain areas to be able to start working on embedded machine learning without necessarily needing to be hardcore experts on all of the little nitty-gritty bits and pieces of embedded machine learning. So understanding how to apply this technology and the situations where it makes sense to apply it and the type of skills needed to pull off a successful project are going to be just as important, or if not more important, than like being able to implement back propagation in like, you know, from scratch in a Python notebook. So I wouldn't worry so much about that type of low level thing when you're thinking about like applications and use cases. But if you are looking at like, oh, I want to get involved with research here, that type of stuff does become more important. So research wise, there's a couple of places that I think are, you know, worth calling out. On the one side is the algorithm development stuff and how can we train these algorithms that are designed for edge devices. On the other side is hardware, like how can you design silicon that's for this type of purpose. And then there's like the stuff that connects it all. So things like techniques for making the most of limited data. There is the tooling like compiler infrastructure that is used to actually turn a model into something that will run on embedded hardware. And then there are the developer tools that allow non-experts to build this type of thing. So no matter what your interest, whether you're interested in low-level machine learning, or if you're interested in building silicon, or you're interested in writing efficient kernels for machine learning operators in C, or if you're interested in building web tools and HTML and JavaScript that implements developer tools that allow people to more easily work with this technology, I think there's like a place in this for you. It's probably one of the most complete technologies. It starts with the silicon and goes all the way up to the cloud. So whatever you're interested in, there are opportunities, and there's definitely going to be a place for you as the industry goes.
Look, thanks so much, Dan. Looks like we hit our time, but I just wanted to quickly call out, I will be lingering in the Discord, so if you guys have any questions for us, I'll make sure we get those answered. But thank you, Marco and Marcelo and Brian, for having us. And it was great interacting with everyone in the chat, and it was super interesting hearing from you, Dan, about the future and challenges, opportunities. And I hope you guys have a great week.
Yeah, thank you, Jenny.
Thanks very much.
Thanks, everybody.
Thank you so much, Dan. Thank you so much, Jenny. That was a great talk. So I'm clapping on behalf of all the participants here. And I think you covered it all. So we're going to get in detail in some of the issue that Daniel mentioned right now in the next few days, this week. So super great talk.